So we can probably start now. So,
okay.
Yeah, so good afternoon, everyone. So today, as our speaker, we have Dr. Dipanjan Mukherjee, and Dipanjan did his PhD in 2014 from IUCAA, and then he did a couple of postdocs, and the first one was in Australian National University in Australia between 2014 to 2017, and then he moved to Italy, Torino, where he stayed between 2017 to 2019. Since 2019, he is an assistant professor at IUCAA itself. So Dipanjan is interested in various topics. So let's say topics of high energy astrophysics, as well as the simulations of astrophysical fluids over a broad range of scenarios. So Dipanjan will talk about his research today to us. So Dipanjan, welcome, and please share your screen and go ahead with the presentation.
Thank you, Shubhendu, for this very kind introduction. And giving me the opportunity to talk to the Aries audience. It's a pleasure. And so I'll start my slides now. Right. So I will not be able to see any raised hands in between. So maybe I can ask Shubhendu to kindly alert me if there are any raised hands.
Yeah, I will.
Or we can take the questions at the end in case. Okay. So again, welcome everybody. So I'm Dipanjan Mukherjee, and I'll be talking about how relativistic jets from supermassive black holes affect their environments. So the work that I'll be presenting has been is an accumulation of results, ideas, and progress that has been happening over the last few years, starting from my, as Shubhendu mentioned, association with my Australian colleagues during my postdoc, and then moving on to the Italian colleagues. And so this is truly a work of a collaboration where we have been contributing some parts from the numerical side using by constructing realistic simulations of the relativistic jets and their impact on galaxies. Whereas we have also had ample help from our colleagues in the observational domain who've assisted us in understanding and interpreting the connections of the simulations with the observational results. So without further ado, let me go ahead. So before I go into the details, maybe since it may be a diverse audience, a brief few comments about AGN feedback in itself and why we do what we do in the first place. So this idea of AGNs or some energy input from the black hole affecting the galaxy evolution comes actually from the point of cosmological simulations. And when people try to reconcile the mass distribution of galaxies that is observed and one that we find from cosmological large-scale simulations. So just putting in the effect of gravity and let things collapse in the forms of cosmic webs and structures, we usually find that we overproduce massive galaxies unless we have some mechanism of stopping those gas that is lying around to form stars. And this is especially a problem for galaxies beyond the threshold mass. So it usually starts from log of stellar mass from 10.5 onwards. But if you see this dividing line here, this is from the Bauer et al. Paper 2012. So the black points are observed mass distribution of galaxies, and the green and the blue lines are from simulation. So previously, when people had started off this large-scale cosmological simulation, they first put in feedback from stars, stellar winds, supernovae, etc., etc. That worked fine for less massive galaxies, but beyond the mass threshold, it did not work because then you were producing a lot more massive galaxies than what we should, as you see from the blue line. Then it was envisaged that we may perhaps need some more ingredient to put out energy into the system that will prevent the gas from accreting and form this massive cooling flows. And it was identified that the central black hole is a very good candidate, at least from the point of view of energetics, to heat up the gas and provide energy to the surroundings. So over time, a lot has evolved in this field. One of the earliest known papers was this from the Silicon Reese paper in '98, but there have been many, many such papers, both hand-wavy arguments and analytical calculations and more hardcore numerical works as well, establishing that black holes are input from black hole is essential to control the mass budget of galaxies and the galaxy evolution and hierarchical structure formation that we have. And people have also identified two modes of feedback from the black holes by which the black holes can affect their environment. One is a quasar mode, or highly luminous black holes accreting at a rapid pace and then giving out a lot of energy in terms of radiation-driven winds and sort of dispersing the gas in the early phase of the galaxies. And the other is a radio mode feedback, wherein you have large-scale radio jets being produced and they heat up the circumgalactic environment that prevents further cooling flows. So that has been the standard paradigm in a nutshell. But there are a lot of open questions here, and that is what we are trying to address. So although the basic paradigm is set now, the nitty-gritties are and the details of it are still open. Firstly, I want to emphasize that this standard two-mode feedback prescription from black holes, that is a quasar mode and the radio mode, is a highly oversimplification of what the true thing is. For example, it strongly oversimplifies the impact of jets. Now, jets, or the radio mode feedback, has been associated with jets in large elliptical galaxies, which are usually considered to be gas poor. But we know now that elliptical galaxies also have gas. But besides that, we also have radio loud galaxies at high redshift, which are also gas rich. And before these jets, go out to large scales where the radio mode feedback truly happens, which is the circumgalactic environment getting heated up by the large scale jets, the jets have to actually traverse through the galaxy itself. So one of the questions that we have been trying to ask over the years is, do the jets have any effect on the host galaxy itself before it goes on to become these large-scale jets that we're more familiar with? So can radio mode feedback in the traditional way, as we have been calling it, also have an effect like a quasar mode feedback, where it affects the gas in the local galaxy? So there's a blending between the traditional radio and quasar mode. The good thing about the jets are they're very powerful and very large and extended, so they can efficiently transfer energy, momentum, and power from the very nucleus of the galaxy to large scales. So that is not a problem. One problem with the radiation-driven phenomena is the fact that the winds or the radiation drops off as inverse square of the distance. But for jets, that's not the case. The bad thing about jets are they're collimated thin structures, as we see in the radio. So how efficiently can the jets transfer their energy, and over what volume? Is it just a thin central region that the jets can affect as they drill a narrow hole through the galaxy and the gas distribution? Or will they have a more widespread effect? And that, again, that is what we are also trying to address, both from observations as well as simulations. So some of the topics of interest are what I've listed here. Firstly, do radio jets affect the host galaxy, or do they just affect the extragalactic gas, as has been the traditional view of the radio mode feedback from the point of view of large-scale cosmological simulations? And what we must understand is, usually for the radio loud galaxies, this duty cycle argument has been always placed in front of everyone. So, saying that it's the radio phase of the galaxies is usually about 10% of the total lifetimes. This usually happens by counting the number of radio loud galaxies in large-scale surveys and comparing their distribution with the quasars. But this has been highly biased based on the flux threshold of the surveys. So this previous argument of 10 to 30%, depending on which survey you're talking about, usually comes because you are limited by a flux threshold in the radio loud fraction. Now, from the recent LOFA surveys, for example, in the September 2019, a fantastic result, they have shown that if you go below a radio threshold, nearly 100% of the galaxies are radioactive, or they're not radio quiet. they might be radio quiet or done on radio silent. So they have some nuclear radioactivity beyond a lower threshold. So this is the plot that Sabat et al. Has shown, that you can see the fraction of radio loud galaxies reach 100% for lower radio luminosity. So lower power jets are more frequent. And since they're more frequent and more abundant, can they still have some effect in the large scheme of things of galaxy evolution? And of course, what we are always interested in this field is how are stars formed and what controls the process of formation of stars. So how is star formation rate actually regulated in the host? And do radio jets have any impact on them? And finally, of course, observational implication. Again, from the context of star formation, I always like to show this plot from Nisbag by 2010. Forgot the reference here, unfortunately, which shows this is the standard Kink-Schmidt line, which is the black line. And the black triangles are standard star-forming galaxies. However, the red ones are part of a radio loud sample of galaxies called the MOHEGs, where you can see that they are at least a dex or lower in star formation compared to the standard Kink-Schmidt line. So the fact that radio loud galaxies are associated with low star formation, although they have gas, the MOHEG galaxies are galaxies with warm H2, where warm H2 have been observed. So apparently something is causing the gas in these galaxies to not form stars, and they have a powerful radio jet in them. So this indirect correlation, of course, points to the fact that star formation is being regulated in some capacity by the jets. How exactly and to what extent, that is the open question. And of course, what are the observational implications of the jets interacting or affecting the gas distribution in the galaxy? That is what we are interested in. So to do this, what we have been trying to do is run a suite of MHD simulations using the PLUTO code. So this, I'll not go into the details of it, but a unique thing about it is it supports relativistic, hydrodynamic, and the magneto-hydrodynamic solvers that allows us to, and this is special relativistic, these are not GRMHD, it allows us to simulate fast-moving jets, relativistic jets, and how they interact with the ambient distribution of gas. So we've been running a large suite of simulations. I'll go into the details of the exact things and just point out some of the snippets of our result. What we try to do is we try to mimic a gas-rich galaxy at first, where a radio jet will become active at a certain point of time. We usually take the typical value, for example, 10% of the gas mass in 10% of the stellar mass in gas, which is very typical of large-scale galaxies, and distribute that gas in the central regions as a turbulent filamentary structure, clouds as we call them. And we let this turbulent filamentary structure with some initialize it with some random velocity distribution and let it settle down into this filamentary distribution with a core radius about, say, 1 kiloparsec or so, and which further extends up to 1.5 kiloparsec. So this is a turbulent log normal distribution of the densities, and we then inject the jet through this dense distribution of gas and see how it interacts with this gas and what are the kinematics and result thereafter. So the typical domain of our simulations are usually a few kiloparsec cube. We have different morphologies of gas distribution, gas in disks and gas in a spherical distribution, as I'm showing here. The resolution is about 6 parsecs in the simulations. The unique thing about this is sort of a bridge between the really small scale jet launching simulations that we cannot, of course, resolve in this, and then the large scale cosmological simulation, which itself has resolutions of a few hundred parsecs or even a kiloparsec. So we are sort of a bridge between the really small scales and the large scale cosmological simulations. The cosmological simulations cannot explore or cannot resolve this dense gas distribution and structures that we can here. But on the contrary, we also cannot go up to very large scale because it becomes computationally untenable to maintain the same amount of resolution. So I will show you one of the early movies of a jet going through this. So I'll give a disclaimer in front. These are 3D simulations. I'm showing you a mid-plane slice in the vertical direction. So this is density, temperature, and pressure. I hope you can see my my arrow from my pointer. And I will let the movie run now. So you can see the jet initially is strongly interacting with this cloud materials. It is stripping the clouds. And after it breaks out, of course, it becomes very fast. So the initial phase of a mega year or so, the jet is confined within the gas distribution. So this goes into the standard paradigm of young and frustrated jets, which are finding it difficult to get out of this dense distribution. But what is interesting is, although it is escaping, it is destroying some of the clouds. So you can see from the temperature map, the blue is the floor temperature of this simulation, which is set at 10,000 Kelvin. You can see some blue clouds embedded within this hot medium. And the jet, although you can see that it is somewhat collimated in the central regions, the impact of the jet, you can see better from the temperature map, and it is spreading the shocks over a large volume. Not just the central region, but it is shocking almost the entire ISM. And the shocks are percolating through these dense structures and spreading out before the jet breaks out. And this is a pressure map. From the pressure map, you can see it forms initially almost a spherical pressure bubble that is expanding outwards, and then it becomes the standard conical shaped jet plumes as we have usually seen. We can also see some recollimation shocks in these diamond shock formations here, which are very typical of expanding jets. So yeah, so initially the jets do interact with this, and you can see some of the clouds do survive very close to the jet. And what happens is we have radiative cooling in these cases. So that once the shock from the jet hits the surface of the cloud, it compresses and enhances the density. And in the post-radiative phase, the density enhances further. And then what these clouds develop is a thick shell of highly dense material that sort of shields the cloud from further disruption or ablation by the flow flowing past them. It forms these cometary tails, but the cloudlets do survive for a significant amount of time before they break apart. So this is one simulation. What we've been trying to do is capture the different effect of different parameters. For example, I'm showing you here are two simulations of same ISM conditions, but two different jet powers. On the left, you have a jet of power 10 power 45. That's why the symbol P45. And on the right, you have a jet of 10 times lower in power, 10 power 44 Earths per second. Again, density on top and temperature on the bottom. You can see the higher power jet quickly punches through the ISM and goes out. The low power jet remains confined within the central region for a very long time. So traditionally, it has been always been the notion that higher the jet power, the more important the effect of feedback, because of course you are dumping more energy. But what we found after running the simulation was even the lower power jets eventually do break out. And it is not the case that the lower power jets only are confined in the central regions. They are spreading the shocks all throughout the galaxy, all throughout the gas distribution. So lower power jets are also perhaps important to consider in the grand scheme of things of galaxy evolution. But what we usually found was that these jets do not really clear out the galaxy. Again, if you look at the early cosmological simulation of millennium kind of simulations, what has been promoted is once the quasar turns on or the jets turn on or any of those outflows turn on, it completely removes all the gas from the galaxy. And that's how it sort of strips the galaxy of its star forming fluid. And that's how it controls star formation. But those simulations are notoriously lacking in resolution. Once you are resolving these dense structures, you will find that you will need a lot more momentum to push out all of the gas. And this is what we found, that only one of the simulations, at least in this series, had a net radial velocity that is going outwards. In others, the gas on the sides are actually falling in due to the effect of the gravity. It's not that there are no outflows, but the majority of the ISM is not being thrown out by the jet. And what we are seeing here is the effect of something like a galactic fountain, where some of the gas parcels are getting lifted up but they are not escaping the galaxy, so they will eventually fall back in to the galaxy source potentials. Now, we've also done simulations of jets interacting with the gas disk. Now, I'll come with a disclaimer that usually when we think of jets and disks, the standard notion has been that the jet is launched perpendicular to the disk. But do remember, these are not the accretion scale disks that we are often more familiar with in terms of jet launching. These are kiloparsec scales galactic disks, or gas rotating in a standard disk, like a Seyfert kind of galaxy. We also have disk-like rotations in many large-scale galaxies as well. And it has been shown in such galaxies, the orientation of the jet is sort of not correlated with the normal to the disk. So the jet orientation is random, because what happens in the core nucleus doesn't really have to be correlated with the large-scale angular momentum of the disk. So what we did was we did a bunch of simulations with different jet orientation and tried to understand how the results are different. So this is a vertical jet. The middle panel is a jet that is inclined at 45 degrees to the disk normal, and this is almost inclined to the disk. As you can see, the vertical jet quickly breaks out, and then it forms this extended backflows. The backflows come and then impinge onto the disk from the top and below and compresses the disk. So although the jet is not directly interacting with the disk here, it's the backflow that is still producing shocks that will go inside, percolate through the clumpy disk and affect the kinematics as well as the temperature distribution of the disk. On the other hand, if the jet is even slightly inclined to the disks, the jet slows down. So these contours, what you're seeing here, these are contours of beta 0.4 c. The white contours are beta 0.4 c, or the jet velocity 0.4, essentially maps out the fast-moving part of the jet, or the jet itself. You can see the jet really slows down. As soon as it hits this cloud, it slows down, but it is still pumping out energy. Although the jet is slowing down, it is still pushed out a lot of energy. And what it does, it forms like a chimney. It slows down here, but then it vents out the gas through the minor axis, because that is the path of least resistance. So from the point of view of a large-scale observer, this would look like a large-scale outflow, not the traditional collimated jet-like outflow that you see. But the jet has decelerated. Of course, eventually the jet will break out as it clears its path of gas here. But the morphology of this total outflow would be more like a spherical outflow coming out of the central regions. And in our paper, we've pointed out this is very reminiscent of many observed systems, for example, NGC 3079. And in this particular case, the jet is completely inclined almost to the disk. It is disrupting the gas clouds, lifting it above the disk plane. You can see these clouds getting pushed up several few kiloparsecs from the initial location. And again, it forms this large-scale outflow. So different kinds of phenomena can happen, and there are different observational counterparts to this as well. So this inclined 45-degree case has been quite popular in explaining several known observations. I'll come to it later. But even this particular case, where the jet is very inclined to the disk, even in that case, there are examples of it, and we modeled it separately.
Dipanjan?
Yes.
Dipanjan, I think Indra is trying to say something.
Okay. Yes.
Why, Dipanjan, what is so great about this 0.4 c that contours you have?
There's nothing great about it. We just took a basic threshold cutoff to show the contours.
Okay, and what is the injection speeds?
The injection speeds are gamma 5.
Gamma 5, okay. Okay.
Gamma 5 for the 10.45, for the 10.44 it was gamma 2.
Okay, okay.
Yeah. No, this is just for visualization. There's nothing special about 0.4c.
Okay, fine.
Yeah, so as I was saying, there are a lot of observational counterparts to it, and I'll come to that shortly. So as I was saying, what we find in these inclined jets is they launch these large-scale outflows, which progress much faster than the progression of the radio part of the jet, because the radio part would be the central parts where the jet is still confined. And from outside, you'll just see an outflow, a large-scale outflow. And these are the velocity contours, or you can see that after the jet has broken out, it has sort of disrupted the disk, and it is making outflows both above and below the disk. All of this is quite interesting, because now what we are seeing here is even irrespective of the rotation or the orientation of the jet with respect to the disk, it can affect the disk on a global scale, on the scales of a few kiloparsec. Although the jet inlet was only 100 parsec or so, at least in our simulation, the effect or impact of the outflow is over kiloparsec scales. And to also map that, what we did was we computed the velocity dispersion in concentric circles radially from the center. So this is the cylindrical radius. And this is the velocity dispersion that we get at different radii. So initially it is a blue line. And as you can see, just let's focus on the red line, which just gives the dispersion of the shock gas, and the green is the total dispersion. So starting from initial value of 80 that we had initially set up, it jumps up to almost 600 or 800 kilometers per second. So initially, so these are at different times. So you can see that the dispersion is high up to this particular radius and then going up. That's because at that point, I'll stop the movie here, only this radius has been affected. So as the jet backflow sweeps over the entire disk, I'll let it run again, the dispersion spreads all throughout the disk, and the entire disk develops high turbulent distribution. And again, this is very reminiscent of some of the observed cases. For example, this, again, referring to this work, Nesvago 2011, for this particular galaxy 3C326, where the width of the line of the entire disk was found to be almost 1,000 kilometers per second, that she had to fit by multiple Gaussians. And it also forms part of these Mohawk galaxies. So the fact that jets can have a global effect is both seen from observations as well as simulations now. And this impact of jets on the local galaxies does deserve some attention. So now, a unique thing about our simulations has been the unique way we are trying to resolve this jet-ISM interaction and as well as density structures, which gives us a very nice handle of trying to compare with observations and make mock images, which we can then compare with standard observations. And the kind of observations we are targeting are integral field unit observations from resolved structures of jets. For example, on a part of this work is being led by my PhD student, Meenakshi. What she has done is taken an output from the mapping schooling code and tried to understand the evolution of the emission from shocked O3 emitting regions. So this is the one of the simulations where the jet is highly inclined to the disk. And you can see the morphology of the surface brightness distribution of the shocked O3 gas. And she's made then mocked a spectrum and then fit the width of the spectrum to get W80 widths, as one would do in actual observations of IFU systems. And what we found was, of course, at the tip of the jet, there is enhanced W80 widths. That's because that is a working surface of the jet. But there is also enhanced widths at regions perpendicular to the jet. I'm only showing one of this. You can find more details for all the simulations in this particular paper, which is there in the archive. We've just submitted the response with the referee. It's a recent submission. So what we found was the fact that the jet, if you recall, was launching these outflows along the minor axis because the jet was getting blocked, the terminal surfaces of the jet, and it was venting out plasma along the minor axis, also pushing out matter both above and below the disk. And this outflowing matter then adds to the W80 widths and forms these patches of high widths in the perpendicular zone. And this is exactly what was also observed earlier for this galaxy IC5063 by Venturi et al. 2020. In fact, we had predicted this when we had done a dedicated simulation of IC5063 in 2018. And then Giacomo and collaborators observed this with Muse and found this extended structure here. And such kind of widths perpendicular or enhanced dispersion perpendicular to the jet have also now become more common, with many such cases being observed, as I'll come to later on. So this is something, again, with the power of the simulations is we can then try to make mock observation kind of things and try to predict what the observations would look like, and then use this information to backtrace to understand what the actual observations do imply in terms of the physics of the system. For example, in one of these things, what Meenakshi has been finding is we are predicting very complex line profiles from the O3 emitting lines. This is essentially tracing out the kinematics of the region because different gas parcels are moving in different ways. And we often find, and if depending on the location, these double or multi-peaked structures. And what we could identify is these multi-peak structures are happening because if you're looking at the jet from an edge on, or if a jet is face on, you're probing through the volume of the expanding shell, you are sampling a forward and expanding shell. So you're sampling the forward shock and the shock that is going behind you. And that is what you're getting here. It's just that line of sight is probing the shock that is, part of it is coming towards you and part of it is going away from you. And that is what gives rise to this multi-peak systems.
Dipanjan?
Yes.
If I may ask, so how do you distinguish the emission is coming from biconical outflow in the narrowband region or emission from the jet?
So these are oxygen-3 emission. So
Yes.
oxygen-3 is not from the jet. Oxygen-3 is only from thermal shot gas.
Yes. Okay. So, but these lines you are saying, is it O3 or?
These are O3 lines, yes. And these are shocked O3, not the photo-ionization.
Okay. Okay.
So another tradition from this kind of work was the fact that the rotation profile of these galaxies will also get distorted. And again, what Meenakshi showed was, this is a case without any jet. It's a standard rotating disk. And we take a slit, you get this nice rotation profile with some dispersion. But once you have the jet, you can see that the rotation profile has changed. It's become steeper. That's because the jet is inducing outflows and is changing the rotation profile in the central regions where the gas is rotating. It has a peak, and then it falls off and joins the standard profile at the edges. This is also there. For example, if you just look at the velocity field there, and if you try to measure the axis of rotation of the gas, you will find what we find is that since we have radial outflows being driven into the disk, the resultant axis of rotation of the gas, or apparent axis of rotation of the gas, has changed. So this is without the jet. It has a vertical rotation axis, and then here you have a distorted line. So this kind of distortions can be recovered from this kind of simulations, and then what we can do is we can go into resolved observations of the systems and try to identify if such signatures exist, and make some comments about the fact that whether the jets are causing some disturbance in the gas rotation. So several such observational results have come out where some of our simulations have aided in interpreting the results, and they are very interesting in the sense that all of them probe some unique part of this phenomena. For example, this particular work of Henry Zavada using Gemini data, what we found, although the radio jet was about a few hundred parsecs, the compact steep spectrum source in the central region, the warm H2 and the Fe2 shocked gas was very large, has a larger distribution. The iron Fe2 was 300 parsecs in distribution, and the warm H2 was 2 kiloparsec. And we confirmed that this is not due to other mechanisms, but shocks driven by the jet. Again, this goes to the previous case where we showed that although the jet may be compact, apparently in radio, because its path has been impeded, the shocks can spread out and affect a larger region. Another case, this Girdhar et al., what they found again was the fact that perpendicular to their jet, they found enhanced dispersion, again, similar to what we had in our simulations, and we've been part of it. Nicole has been championing some of these cases where we found she found a jet, and this was in fact an initial discovery by an Indian astronomer in IUCAA itself, led by Joydeep Bakshi, where a spiral galaxy has a large-scale jet. And Nicole has followed it up with ALMA, and we also have other data in the pipeline. What she found was the inner edges of the gas disk in ALMA has high velocity dispersion. Again, very reminiscent, at least from a qualitative perspective, of what we find in our simulations, where the jet has a working surface, but a cavity in the center because it's been clearing out the gas that's been flowing out. Also, more recently, there was this nice result by Raffaella Morganti and her students, and we are also involved in it, where they found that there's a young jet in a system. This is a recurrent activity, so there's a large-scale radio lobe as well, and the young jet is pushing out gas. And what Raffaella found, and Raffaella and Suma had found there, was the fact that almost 75% of the central reservoir of gas in the central few kiloparsec is in the outflow, and that outflow is being driven by the jet. So this was published in Nature Astronomy because this is one of the only unambiguous detection of a radio jet that is powering this outflow. because other means of providing the energy from the AGN or star formation driven winds have been ruled out because it's a low luminosity AGN and the star formation is also low. So it is a jet that is powering this outflow, and it is clearing out 75% of the gas in the central reservoir. So jets do affect the central regions of gas in the galaxies, and I think more attention is required on how jets fit into this large-scale picture and not just the large-scale environment. And of course, when we're talking about observations, we should also mention this, what happens to the radio. And so one thing that we, of course, probed here is the free absorption by the intervening medium of jets, and very popular to explain this curved spectrum. And what we found was indeed some of our simulations can reproduce this curved spectrum. An evolution of the spectrum as the jet evolves from a GPS kind of source of gigahertz peak spectrum to a large scale source, which is the compact Steve spectrum. So I'll end here. But it's not just about the observations. We're also trying to understand the different aspects of physics involved here. And that's, again, a work being led by another student of mine, Ankush Mandal, who's trying to understand the impact of these jets on the star formation of the host galaxy. So what we've been trying to do is improve the standard prescription of understanding star formation by improving upon the theory of how you compute the star formation rate in such systems. In standard cosmological approaches, the way you calculate star formation is you put a constant fractional threshold of the mass in a particular region divided by the free fall time, and that becomes your star formation rate. And as you can understand, this free fall time is just proportional to density itself. So star formation rate is just purely a function of density. But that is not completely true, because we know from more detailed analysis of star formation, turbulence regulated star formation prescription is often used in understanding cases for molecular clouds. Turbulence plays an important role, and that is what we've been trying to do. So in an earlier work, what Ankush did was take one of my simulations and identify star forming regions using a clump finder, perform some statistics on them, and applied this this turbulence regulated star formation prescription from a completely different field of work using the prescription by Mark Krumholz and Christoph Federer. And then I identify what will be the impact on star formation rate. What we found was indeed the velocity dispersion does increase quite significantly in these clouds by the impact of the jet. And the virial parameter, which is a ratio of the kinetic energy to the gravitational potential energy, that increases. So if the virial parameter is 1 or less than 1, then of course, then the system is star forming. But as you will see, but just from very simple arguments, which I have mentioned in my review here, it does not take much to change the star formation rate. For example, a slight change in the virial parameter by a few factor of 10 or so, and a slight change in the Mach number of the gas can lift it from this zone, which is star forming, to here, which is not star forming. So this is what it shows, that if you increase the dispersion in this, the star formation does decrease. So what Ankush finds is the fact that, so this is the evolution of the total star formation rate in our simulations. This is the gray line is the case without the jet. So it increases. It has some ups and downs because it's still a turbulent disk and it's settling due to gravity. And these are the simulations with different sort of inclinations. The ones with are more inclined, they show an initial decline in the star formation because the jet is strongly interacting with it and inducing turbulence. But what is interesting, at least in our case, was after this initial decline, it starts rising again. So what happens here is, as long as the jet is confined and strongly interacting with the system, it is raising the velocity dispersion and reducing the star formation rate by a factor of few. But as the jet escapes, it decouples from the system, and the velocity dispersion then decays naturally. For our case, of course, it is regulated by the numerical viscosity. We can't help that. But in a standard case, it will still decay naturally as is expected. And then the star formation rate will keep on rising. So when we look at the distribution of star formation rates as a function of density, what we identified are these two different patches. One is where the star formation rate is slightly reduced. So the gray points are the standard star forming clouds from a no jet simulation. These regions here, and these are mostly from the outskirts, so radius more than 1 kiloparsec, they have reduction in star formation rate. And the reason is because they have been affected by the turbulent injection of velocity dispersion by the jet. But region close to the jet, which is within 1 kiloparsec, they, as you can see, that they have an enhanced value of star formation not seen in the gray dots. The gray dots are, again, to repeat, the star formation from the simulation without the clouds. So we can have both an effect of negative feedback on the outskirts and more positive feedback here in the central regions where the jet is directly impacting the gas and enhancing a star formation rate. Again, the results are published in Mundell 2021 if you are interested. I think I'll skip this because I'm slightly running out of time. So in this new phase of study, what we are trying to understand is probe this question deeper. And before we again go to large-scale simulation, what Ankush has been trying to do is develop a new self-gravity module in PLUTO. So he's implemented that, a new recycle multi-grade Poisson solver in PLUTO. We are still working out the details, a few of the details, and yet to publish it. But then what we are trying to understand whether self-gravity becomes important at some point. So Ankush has been performing a few simulations. So this is a fast shock that runs through a cloud. So these are cloud crushing experiments. And this is a shock of 4,000 kilometers per second. What we found was that the case with and without self-gravity has not much of an effect. However, with a slightly slower shock, and this is with 400 kilometers per second, what we found was self-gravity starts to take over. So the cloud is not as easily destroyed as the previous case, although it is getting affected. But if you look at this plot, which is, I'm plotting again the alpha virial, which is the ratio of the kinetic energy of the turbulent kinetic energy to the potential energy. This is the case I showed in the first case. So this is with and without the self-gravity, it exactly matches. But for this case, what I'm showing here, this particular case, which I've labeled no gravity and with gravity, without gravity, it follows a line like this, and with gravity, the alpha virial significantly decreases by an order of magnitude. Which means that if you start including other external physics into whatever analysis you've done earlier, some of our results will start changing. And so understanding the impact of jets on star formation is still an open question. So far, as in, again, just to reiterate, people have been doing very simplistic calculations of star formation just based on density thresholds and cutoffs. And more physics needs to be put in to understand the impact of this outflows on the star formation rate. And that is what we are slowly building upon. So just to quickly summarize this part, in the last 15 minutes, I'll slowly switch to something else. Jets couple strongly with the host's ISM. It launches fast multi-phase outflows, but these outflows do not escape the potential of the galaxy. Low power jets are important, to not discount them just because they have low power. They are more numerous and they can also affect a large scale region. And although you can perhaps see only a small part of the jet in the radio maps, does not mean that the effect of the jets is confined only to that radio image. They can have a more extended effect, as I showed in some of the observed results that we have seen so far. And both negative feedback due to turbulence and positive feedback due to compression can happen in the same galaxy. So clouds in the direct path of the jet can get compressed. They'll all, of course, lose mass because they'll be stripped of the mass by the flow of the jet. But if they're large enough, this compression can actually trigger a star formation. And we have examples of that, for example, in the Minkowski objects and many others. But it can also have negative feedback. For example, if you have inject turbulence on the outer regions, it can temporarily reduce the star formation rate for a few megayears or so. But of course, these effects are not long-standing. As soon as the jet sort of decouples from the system will start bouncing back. So what will end up is different stellar population histories at different spatial locations in the disk. And if we have observational resolution to map those, that would be one of the tests of this kind of simulations. So I'll slowly switch gears to a different kind of work that we've been doing in the last few years now. This is not related to the multi-phase outflows that we have been discussing so far, but more towards understanding the evolution of the jets themselves and the emission of the synchrotron radiation from such systems. So we've recently developed a new numerical module for the PLUTO code, which launches non-thermal electrons along with the fluid flow. And for each of this non-thermal population of electrons, we solve the phase space equation of their evolution, duly accounting for radiative losses due to synchrotron and inverse Compton interaction, as well as shock acceleration. So we solve this full, the phase space formalism. And what this essentially gives us is this. So from the standard synchrotron expression, we know that to understand the synchrotron, we have to integrate over the energy distribution of the non-thermal electrons. And this is what we can now better understand from the simulations by injecting these non-thermal electrons along with the fluid flow. And as I said, we also have subgrid prescription of modeling acceleration at Fermi acceleration at shocks. So Fermi first order acceleration. And we have taken the cues from different semi-analytical works to understand how this microphysical acceleration will work. So we've done this for a couple of simulations now. And again, these simulations are also quite expensive because at the end of it, you launch several tens of millions of these hybrid particles along with the standard fluid, which then maps out different locations. And of course, the evolution, the spectral evolution of these particles will depend on the local properties of the fluid, because the synchrotron emission depends on the local magnetic field distribution. So how these particles will age and how their spectrum changes with time depends on the local properties. So if you have a non-homogeneous distribution of fluid due to, say, turbulent properties inside the jet, that is something that we can better characterize now with this kind of simulation. So I'll show one of the simulation. Again, now here we don't have those clouds or interaction with the distribution of gas, but you have a standard in a conical shaped jet and its cocoon. And this is the plot of the particles overplotted along with the density of the jet. And what I'm showing in color here is the end of this, or the largest Lorentz factor of a spectrum of a particle. So what you can see, first of all, to explain what you're seeing here, the central part of the jet is filled with highly energetic particles with gamma going up to 10 power 8 or 9. These are very short-lived, of course, because this is the largest one, because they'll decay very fast. But the central part of the jet, of course, has highly energetic particles, as would be expected, because they are getting accelerated by the recollimation shocks going along the jet. They go to the head, where they are shocked again by the strong shock at the head, and then they will stream down. And as you can see in the backflow, they're mostly filled with older particles with cooling properties, so mostly blue or black. So it's the standard evolutionary picture. But what's interesting now is if we don't have such a regular stable jet, if we have MHD instabilities that induces turbulence inside the cocoon, then the particles can take different tracks. For example, this one particular simulations, I've traced out a few particles. Again, you can see the more detailed analysis in our paper in 2020 and 21, where this particle takes a loop and then goes back into the jet stream and then finally comes out. Similar for here. And these are, of course, due to local Kelvin-Helmholtz vortices that appear as the jet axis of the jet wall is interacting with the cocoon and forming local shears. So this is the evolution of the emission for two different radio bands. This is one stable jet with just a hotspot, and this is slightly fatter jet. But I just wanted to show how that we can now produce this kind of a system where we can get the hotspot and the structure of the jet. But what's more interesting, not just producing these images of the jets that is expected, is trying to characterize how the synchrotron evolution or synchrotron emission is related to the local fluid properties. For example, these two particular simulations where we have in the left case, we have a lot of internal shocks inside the cocoon of the jet because of local turbulence and the way we have launched the jet. In this particular case, there is less of such internal shocks. What I'm showing here in the volume rendering are the shock surfaces. In the standard evolutionary picture, the particles will hit the hotspot and come down through these shocks in the backflow and get reaccelerated. So this particular case, all of these particles in the backflow will, if they pass through the shocks, they will get reaccelerated. Whereas in this case, it will form the standard picture where the particles got only accelerated at the hotspot, and then as they come back down, they just cool down due to the inherent magnetic field. So what this means is internal shocks can have an important contribution to the spectrum. For example, you can look at the initial spectrum, it's a power law of the cooling property. But then as it goes through different shocks, this particular particle, the nature of the spectrum significantly changes. So here at the shock 16, you can clearly see there are two different power laws. So of course, this is the exponential cutoff due to cooling. But these two different power laws are due to the fact that it had crossed through two different shock strengths. And they have imprinted their shock properties of the diffusive shock acceleration properties onto the particle. The resultant particle is actually not a power law, but more like a parabola. And we can explore this and the impact of different jet instabilities or MHD instabilities. For example, this is one case with we have Kelvin-Helmholtz instability. So the left hand is a more magnetized jet. Sigma is the ratio of the Poynting flux to the jet flux, but let's not go into the details of it. This is more magnetized, this is less magnetized. Less magnetized jets do not have the magnetic support of the central region, and that's why it is more susceptible to Kelvin-Helmholtz modes. I can see that I'm showing the distribution of the magnetic field is very patchy distribution, and you don't have a core jet axis as you have here, and this is because of the Kelvin-Helmholtz. Again, already been shown in Mignon in 2010, but what we can now do is understand how this kind of instability will affect the synchrotron evolution. Another is the kink instability, where the jet end bends as you increase the magnetic field. And of course, the growth rate of kink modes depend on several different factors. In this particular case, it is more apparent, where as you can see that the jet head has bent. And we can then image the impact of this and then you can do all sorts of analysis of the polarization, etc. This is a nice rendering in the U band, synchrotron emission in the U band. You can see the plume of the structure. But what is more important is now we can identify what happens at different locations and how it impacts the spectrum. So what I'm plotting here is the total cosmic ray electron spectrum at 3 different locations. One is the jet head. It's a simple power law going up to high energies. But if you look at the one in the portion here, which is the backflowing region, you clearly have imprints of multiple population of electrons, which has suffered through different shock surfaces. And each shock has different shock strengths. So they have different levels of acceleration and different power laws. And all of this is getting imprinted onto the electron spectrum. And this electron spectrum will then give you the synchrotron spectrum. So all of this gets correlated with how the fluid instabilities are being built inside the jet. And another interesting property that we are finding here is these are the total spectrum of this unstable jets and stable jets. So let's take, for example, this particular case. It has initial power law, and then it steepens due to synchrotron decay, but then it rises up again. And this secondary rise is because of particles being accelerated at the sites of fresh shocks inside the cocoon. In the stable jets, you don't have such secondary rise. This is because the stable jets don't have internal shock surfaces where you can have reacceleration. So this is an effect of 2 distinct almost electron population. One is the general population of electrons in the cocoon, which are standard cooling electrons. And the other electrons at the different shocks, which are reaccelerating the fossil electrons that are flowing in the backflow and energizing them. And this kind of thing has also been predicted by observations. For example, this particular case of PKS Parks 0637 by Meyer et al. 2015, where people have observed this point in X-rays, and it was initially thought to be a signature of ICCMB, but that was ruled out because there was no Fermi detection. There was a very strong limit. So it has been speculated that it's a secondary electron population with the different properties of the electrons are more high or more energetic electrons that is causing this X-ray point. Similar observations by Giulia Migliori in 2020. And this is what we are also finding from our simulation, that there are different distribution of electrons inside the cocoon. Some can get reaccelerated at internal shock surfaces and produce this high energy emission. And these properties would be very different, or the morphological distribution would be different from the standard radio distribution. Because in the high energies, as you are seeing here, for example, the color-coded images from, this is from the Migliori 2020 paper. The color is in X-rays and the contours are in radio. There's a clear shift between the radio and the X-ray. And that is because the radio maps the total electron distribution, whereas the X-rays only map the shock surfaces. just to summarize this, what we find is there can be different kinds of instabilities inside the jet. We can have kink modes instabilities, which causes bending of the jet and on extended shock structures. These are 3D volume rendering of the shocks. Or we can have Kelvin-Helmholtz instabilities and local internal shocks inside the jet. And the particles flowing in the backflow will get accelerated here. And these shocks will leave that imprint on the particle spectrum, which will in turn affect the electron, the synchrotron spectrum that we observe. So summarizing, what I think I have tried to impress is we need different kinds of simulation techniques to understand different aspects of this problem of how jets impact their environment and what we can learn from them in terms of the physics of what is happening there. But not just the different kinds of simulations that are important, we also need different kinds of observations. We need multi-wavelength observations to understand whether it's starting from the cold phase to the warm and the highly ionized phases, as well as more energetic populations from the radio synchrotron emission. And we need spatially resolved simulations as well as spatially resolved observations to have a greater insight of what is happening at the core of these galaxies when the jets are still embedded inside the galaxies. So I'll end my talk here. Thank you.
So let's thank Dipanjan for this wonderful talk, and those simulations are really beautiful. So now we have time for question and answer. So kindly raise your hand or ask the question directly to Dipanjan.
Dipanjan.
Yes.
Very nice talk.
Thank you.
Okay. Part of it I heard in the ASI, and but I have one of the questions I am to ask is that you have now this module where you can study the particle accelerations, right?
Yes.
So in your simulations, did you find out that some of the particles are leaving the jet and following the magnetic fields and becomes precursors of cosmic rays or something?
Yeah, so of course we have particles. So the particles follow the standard trajectory of going to the jet and at least reaching the head shock.
Right.
But then after that, they can follow the standard streamlines and just cool down, or they can get reaccelerated at the shock surfaces. Now, whether they are precursors to cosmic rays particles or not, that's a different question, because so far we've only been focusing on the electronic particles, that's electrons.
Oh, okay.
We haven't done the protons.
Okay.
Yeah, so the proton acceleration is still not there. We've been discussing with a few people, but we have to include that.
Okay, all right.
Raj, please go ahead.
Yes, I have one question related to your simulation where you showed the feedback with the interaction with the disk of the jet. So like there are different evolutionary phases of the jet. So when it is launched, so like when the jet is launched from the disk, it is heavier than the medium surrounded by the accretion disk, right? Then it evolves, and then ultimately the ambient medium.
I'm not so sure about that, because we are talking about relativistic jets here. So if you're talking about on scale, these kind of jets would mostly be Planck's night jets, which would be left on.
Yeah, but like in terms of density contrast, when the jet becomes supersonic and when we study its evolution in the ambient media, so
so then
generally it is
even then in that case we are not sure how much of mass loading actually takes place. So I'm not sure whether the jets the density contrast would be more than one.
Yeah, so like in your case in these simulation, so what is the typical density contrast?
It's much less than one.
Much less than one.
Yes.
So
even I'll start off with a density contrast of 10 power minus 3, 10 power minus 4. Of course, it mixes with the ambient medium eventually, but even then the density contrast is less than 1.
Yeah, so like the thing is, for example, the higher power jets are like they are traveling in a collimated path, so in comparison to low power jets. So similarly, if we have like heavier jets, so they will not affect the ambient the disk much, right?
Why will the heavier jets not affect the disk?
So like the heavier jets, let's say the jet is heavier than this whatever the surrounding medium it is propagating. So then like the evolution is like much more like a ballistic jet, right? So it goes like a bullet.
Yeah,
So
but then if it is heavier, of course, then it has more propensity to disrupt the.
yeah, but when it is hitting your this clumpy environment, so
Yes.
like whether
No, if it is heavier, then of course it has more momentum than the environment. So it will, if it, as you said, is ballistic, that means it will tear apart anything that comes on its way. So it has more impact if it's heavier. Of course, these jets are not heavier.
Yeah, these
jets are lower, but they have higher momentum because they're relativistic.
Yeah, it's because of this effective gamma square.
That's right.
Yeah. Okay. Okay, and another question is like where you showed this the turbulent cocoon, and so where these particles are being accelerated. So like what are the parameters like which can lead to these type of turbulent cocoon? So whether this is the initial setup you give in the simulation or the parameters of beam
depends
itself?
on a couple of points. One is, as I said, on the magnetic field distribution.
Okay.
If the magnetic field is low, then Kelvin-Helmholtz instabilities are have a higher growth rate. Of course, it depends on the orientation of the magnetic field, but in general, even for a turbulent distribution, it depends on the some will have higher growth rates. So that is one thing. Another thing is if your Mach number is high, or if you have a higher sound speed, let me rephrase. If you have higher sound speed, then the perturbations can travel faster.
Okay.
So even in that case, if I launch a jet with a slightly overpressured jet, for example, compared to the initial value, then what we find is, again, we have lots of local internal structures. And again, this is not a new result. It's already been shown in previous works that we have more internal structures. What we are showing here is that actually impacts the particle acceleration.
Okay, and what is the initial configuration in terms of pressure, whether they are pressure match jets or?
So initially we launch it at as being in pressure match with the environment for most of the cases. But as I said, there are no constraints, to be honest. Because in any way, if you launch it once, the pressure, it builds up in a small domain. So it immediately becomes overpressured compared to the environment.
Yeah, okay. Okay, thank you, sir.
Thanks, sir.
Dipanjan, so observationally, at what fraction of objects do you see this high inclined jet?
There's a work by Gallimore in 2006, and this is more for Seyfert's, where they show that it's that correlation is random.
Okay.
So there's no correlation between the inclination of the jet with respect to the large-scale kpc scale disk.
Okay.
Because the accretion of the central regions can happen at a different pace compared to the large-scale gas dynamics.
So are you starting more objects using IFU, Gemini, or something?
So we are our group mostly does a simulation, but we are always open to people who can help us in understanding this from an observational perspective. So we have collaborators and who are trying to look at this with integral field units. You say, but what we need is high resolution data from these systems. So yes, we are always on the lookout for such opportunities, and we have collaborators who are doing it as well.
Okay, so are there any further questions from audience? Okay, so if not, let's thank Dipanjan again for this wonderful talk. And we hope that you could have visit us here in person and interacted with us. But anyway, we'll see later this opportunity.
Yeah, Dipanjan, visit.
Yes, Indra, I'll be very happy to. Haven't gone to Aries yet. Hopefully, we'll get to see the views someday.
Yeah, do visit.
Yeah.
Okay. Thanks a lot, Shubhendra.
We wanted to have you in person, but anyway, we'll see later again.
Hopefully later.
Okay. Bye. So with this, we'll log out today, and we'll meet you next time. Bye.